a ZK proof is really relating that this set of inputs is related to this set of outputs using this particular program. I like to call ourselves as a ZK wrapper for Ethereum block space. You will access the Ethereum block space via this ZK layer and nothing else. You have like Ethereum block space here, and then you kind of zoom out this aggregation layer, which is offering you much more block space effectively. And on top of that, you have these rollups, which then again offer you much more block space. It's kind of multiplying as you move up the layers.
I'm here with Garvit Goel. He's the founder of Electron Labs. They're a universal proof aggregator that produces superproofs, and the goal here is to significantly reduce the cost of proving on-chain. Before we get started, be sure to subscribe to get notified when new episodes drop every week. And remember that none of what is discussed here on the Interop should be considered investment or financial advice. And also know that Interop Ventures is an investor in Electron Labs. And if you enjoy this content, please consider staking with us. We're validating on Evmos, Quicksilver, and Osmosis. Just look for Interop in the active set. Hey, Garvit, thanks for being on the show.
Thank you for having me. I'm excited to be here.
Yeah, absolutely. So let's get right into it. How did you get into ZK, and what made you want to focus on solving the problem, which is that ZK proofs are so expensive to verify, especially on Ethereum?
Yeah, thanks. So I think our journey started like almost 2 years back. We were just trying to, we were a bunch of people in New Delhi. We were just trying to experiment with some ideas and build something on chain. Like we didn't really have any ideas, but we wanted to do something on chain. And as we started to work towards it, we started to look deeper into the protocol side of things and how consensus works and all of that. And ZK was this natural attraction to us. It seemed to solve all the problems that actually plague the current blockchain designs and seem to solve all of them. So we just kind of gravitated towards that eventually. And once we were into it, we could see that's really the right place to be, and been in that ever since. Over time, we started to feel that as we were building things on Ethereum and ZK, we started to notice that most of the use cases that actually use ZK, it's extremely expensive for them to verify these proofs on Ethereum. And no one really talks about them. People are talking about hardware acceleration, GPUs, and all sorts of stuff. But nobody is talking about the cost of verifying these proofs on Ethereum. While that, in my opinion, happens to be the limiting factor right now, when it comes to ZK-based products. So we thought, okay, we need to really address this, and we need to figure out a way to reduce this cost significantly before anything else becomes possible in ZK. Yeah.
What are some of the other attempts like made by, say, other teams or even on the sort of core Ethereum client to reduce the cost of verifying ZK proofs?
Yeah, I think the very first one was actually the EIP process, where a precompile was added in the EVM to enable proof verification much more cheaply, right? So without that, it would be even more expensive. So that was one of the first things that the Ethereum community, the core developers really made happen. And that was really done to enable the ZK scaling roadmap to happen, right? But over time, even after that precompile, it still is significantly expensive. So we need to do a little bit more work here. I think we kind of maxed out the EIP process here. So yeah, we need to start looking elsewhere, other approaches to really reduce the cost. Yeah.
Yeah, understood. And what is it about ZK proofs that make them so expensive to verify on chain?
Yeah, I think, if you want to do any native computation, let's say verify a proof on your laptop, it wouldn't be really that expensive. It's fine, all right. I think doing anything on chain, especially Ethereum, is generally very expensive compared to any other platform of computation. So naturally, ZK proofs have also turned out to be a little bit too expensive.
Yeah. Okay. Well, let's maybe take a little bit step back here and maybe just give a little bit of a ZK crash course here. I recognize like these topics are widely discussed, but I think for some people, getting a little bit of clarity on like what is a ZK proof and what's a ZK-like client would be helpful, and certainly also for me, like always helpful to get a new perspective on how ZK proofs are used in crypto. So, yeah, what is a ZK proof, and how are they verified on chain?
Yeah, I think so. If you look at any ZK-based product, there are essentially two operations that are happening. The first one is the proving side, ZK proof generation, as it's also called, And the second part is ZK proof verification, right? So ZK proof generation happens on off-chain machines. It could be your mobile phones, browser. Typically, it's some sort of large machine that somebody's running on AWS or a GPU somebody running at home. That's where it usually happens, proof generation. Proof verification happens on a smart contract, typically Ethereum, right? So that's kind of the two operations. Now, what a ZK proof really is that it's really encapsulating a computation, right? So let's say certain inputs, right, or numbers, let's say, were used and some operations, computational operations were performed and then to produce an output, right? If we just kind of do that abstraction, a ZK proof is really relating that this set of inputs is related to this set of outputs using this particular program. It's really telling you that. I mean, in a general sense, if you wanted to check that relationship between these three parameters, you would ideally be required to run that computation yourself. That's how computation has been done before ZK. But ZK really allows you to have a proof that these three entities are related to each other without actually you having to run that computation, that program yourself, right? So it's really, in a way, you can say it's computational compression. So you don't have to perform that computation anymore in order to check that relationship between that input-output. It's really not a very simplified explanation, but it's really one of the, it's really hard to go simpler than this. Yeah. So
No,
yeah,
that's really helpful.
Yeah.
And the way I sort of describe ZK proofs is the ability to prove that someone else did something that ends up that you can verify the result. I mean, I think that's also like a very simple way to describe them. Now, in crypto, ZK proofs are used for a number of use cases. Like privacy is obviously one use case, but increasingly over the years, ZK proofs have been used to in the context of scaling and rollups. Can you briefly describe like the relationship between ZK proofs and rollups?
Sure. So what happened is that ZK proofs were originally designed for privacy. But what people realized that they kind of ended up having this additional property where verification of the proof is significantly cheaper than the computation itself, right? So you have this computational compression property again. So you can perform some computation elsewhere and then verify it on your chain for a much lesser amount of resources. So again, with blockchains, the challenge has always been how do we reduce the amount of computation we need to do on chain? So that's what rollups ended up being, that you do perform computation elsewhere outside the chain on AWS, on some other third-party server. And the proof of that is simply posted on Ethereum. So it really allows you to offload computation without increasing trust assumptions.
Right. And so here, like the issue again, like coming back to the core problem is that blockchains are inefficient when it comes to executing computations. We have a limited amount of sort of computational bandwidth on a blockchain due to the fact that they have all these other properties, they're decentralized, they're censorship resistant, etc. That makes computation more expensive. And so offloading the computation to an off-chain, whether that's like a roll-up or like an off-chain computer, you could just verify that computation on chain and then continue to run the blockchain as though that computation had been run there. So in terms of the trust assumptions, I mean, are we operating in exactly the same trust assumptions, or are there other trust assumptions that one has to take into account when verifying a ZK proof and integrating the outputs of that computation into their application, whether that's a DeFi application or whatever?
Yeah, I think if you talk about simply the ZK primitive, the cryptographic primitive, right? If you forget all the systems rollups around that, the primitive itself is completely trustless. I think people will not really debate that, in my opinion. That when you are offloading this computation, you get full mathematical security. There's no sort of dependency on any stake, particularly for this security model to kind of hold. But this is only true as far as the cryptographic primitive goes, the ZK proof itself. When you build an entire sort of network around that, which is the rollup itself, then there are some sort of limited sort of, I wouldn't say trust assumptions, but nuances that kind of come into picture, where there are sort of these edge cases where, for example, that mass exit problem and all of that, where there's some dependency on who's generating the proof. So again, like I would, it's really hard to quantify what those issues even are. And this debate, as you know, is always ongoing on Twitter. What are exactly the trust models for rollups? And things get a bit subjective there. But I would say that, yeah, like getting something done completely on chain is obviously slightly better in terms of trust assumptions. But rollup model, in my opinion, at least, is quite good enough to really do that. And again, the primitive itself is perfectly trustless, in my opinion. Yeah.
Sure, but like I think that you made a good point. It's like when you build a system that has multiple interdependencies, you introduce some other trust assumptions that don't exist in the primitive. What are some sort of key points or some key connections between those different components of the system that introduce these nuanced trust assumptions, as you put it?
Yeah, right. So I mean, let me try to explain. It's really a very kind of hard to explain thing. So I think if you were to, let's say, go case by case, like for example, one of the sort of trust assumptions is that, let's say, the underlying chain, which is Ethereum, goes through a forking process, right? How does the rollup decide which fork is the one they want to be on, right? It really comes down to the governance of that rollup deciding which fork is the right one, right? So that's for example one example where you have some dependency on the governance of the rollup itself. Now, how do you define the governance of a rollup? That itself is a question, because whether the rollup governance is happening on chain or is it happening on the rollup itself, the governance contract particularly, right? If it's happening on chain, then it could probably be two different governance decisions happen on the two forks as well. If it's happening on the rollup itself, then what are the liveliness properties around that? Because if the chain is going through a forking process, is your rollup actually going through a liveliness issue as well while you figure out which rollup you're on? So these kind of edge situations exist. I think forking process is really one of those biggest issues where it becomes very clear that there is a kind of a different trust assumption over here. We can quite starkly see the difference in the models here. If you talk about a general ongoing process where the underlying chain is not really going through a forking process, I think, in my opinion, you're broadly in the same category, except the fact that you have some dependency on the people who are actually generating these proofs and posting on Ethereum. So which is also referred to as the sequencer, and the single sequencer and multi-sequencer debate is always happening on Twitter. So if you have a single sequencer, right, which is basically just one person who has the absolute right to generate these proofs and submit to Ethereum, the risk is that this sequencer can simply decide not to post proofs at all. It could simply go offline,
Yeah.
and nobody is now able to generate these proofs anymore, right? So in this situation, again, what's the roll-up model in terms of being able to withdraw your funds kind of becomes a question. Usually roll-ups do have a mechanism, where mass exit problems are kind of avoided. But again, like if you have a single sequencer, you can have sort of these issues. This becomes very starkly clear when you talk about the data availability side of things. So for example, let's say I have $100, in my account on a roll-up. The proof of that is definitely posted on Ethereum. But the fact that it's $100, what if I lose that data? What if everyone loses their data? So generating that state back on Ethereum for progressing the rollup forward becomes a little bit hard. So that's why having that data available, which what these DLAs actually do, becomes a bit of, if you don't have that data available with you, the rollup sequencer can't really run away with your money, but it can make sure that you are not able to access that money anymore, right? So these
Yeah.
kind of sort of situations exist where a rollup model is kind of not as secure as the underlying chain.
Right. So with rollups, of course, we have this issue of data availability that is basically like the core of how a rollup operates. It needs to have access to the data. And then there's also this sequencer problem where if you have a single sequencer, there can be a censorship or liveness problem here where the sequencer can censor transactions, voluntarily or involuntarily.
Yeah.
And that's also one of the risks. Okay. And one last thing here before we move on to Electron and the aggregation product. A ZK-like client. What's a ZK-like client, and how does it operate in this scheme?
Sure. So before ZK light client, let's understand what a light client is, right? So let's say you're sitting outside the chain and you want to verify the transactions happening on the chain. You want to verify if they're valid transactions or not. So usually chains like or well-designed consensus algorithms like Tendermint and Ethereum, they're supposed to have this light consensus where if somebody wants to verify the validity of a transaction, they can do so without running the full consensus from Genesis, right? So they should be able to run a lighter form of computation to verify this computation. That's what a light client or a light node or a light consensus verification mechanism is. ZK Light Client is the ZK proof that the light consensus was turned out to be valid. So it's basically, so ZK Light Client can also be looked at as an ultra light client. It's an even lighter version of a light client where you get a ZK proof of validity of the light client execution itself. So the reason you need a ZK Light Client is because ZK Light Clients are so light that you can run them as smart contracts. So you can verify the consensus of one chain inside the smart contract of another. Like, imagine trying to verify Solana consensus on an Ethereum smart contract. Like, you can't do that. The computation requirement is massive. But if you could actually reduce the entire Solana consensus to a ZK proof, you can verify Solana consensus in Ethereum for like $50, which is much more practical than otherwise. Yeah.
Right. So here the application here would be to say, like, if you had an application on Ethereum or on any chain that wanted to say verify that funds were transferred into a contract or were locked on Solana, you could verify the state of Solana and then have the confidence that those funds were locked over on Solana. And this we'll get into later has implications for ZK IBC, which obviously relies on funds being kind of like segregated or locked before they can be minted on another chain. Very cool. Yeah, thanks for that. I think that's going to be very helpful for a lot of people and sort of sets the context for the rest of the conversation here. So Electron, I think previously was focusing on building a ZK IBC implementation, but you guys have since moved away from that to focus on this kind of key problem, which is the cost of ZK proofs. And you've built a ZK proving aggregation mechanism that creates a superproof. I love this term, superproof. So what is Electron doing here? Like when you're aggregating all of these proofs and building this superproof, what's actually happening in the background and how are applications interacting with the superproof?
Yeah, absolutely. So let me just give you context why proof aggregation was needed in the first place. So as I said, you have these ZK Light clients which make it really cheap to verify consensus on Ethereum. But even after you have a ZK proof, even ZK proof verification it's much cheaper, but it's still quite expensive at the end of the day. Like based on the current gas prices, it has been fluctuating between $15 to $60 in the last couple of weeks and months for verifying one proof. Now, if you want to verify ZK proofs on Ethereum very frequently, let's say once every Ethereum block, this turns out to be like $200 million every year. So, I mean, if you have a ZK-based product, it's going to be really damn expensive to operate that. So we learned over the past 1 year while working with ZK IBC and ZK Light clients that it was not just limited to these use cases. All use cases using ZK, be it privacy, be it ZK micro rollups, be it ZK-based DA bridges, all of them have this problem of extremely expensive proof verification on Ethereum. So we have reduced the computation very significantly, but it's still quite expensive. So that is when we really realize that we need to get this cost of proof verification down. So this is where proof aggregation comes in. And in my opinion, it's really the only way to reduce the cost in the long run. That's kind of really only the foolproof way. So proof aggregation works like this. Rather than everyone submitting their own proof on Ethereum, we collect these proofs from different protocols. We aggregate them together into a superproof, and this superproof is then submitted on Ethereum. What this allows you to do is that now the cost of the proof verification on Ethereum is shared amongst all these different protocols, and every single protocol has to pay like 1% of the fees that they were paying originally. So a drastic multiple orders of magnitude reduction in the proof verification costs on Ethereum. So that's where we really are. So the super proof is simply the aggregate proof of all the other proofs that may be out there. Yeah, that's kind of what we're doing at this point.
Okay, and so when you're constructing a super proof, you're taking all these proofs and aggregating them together into one proof that anyone can verify and sort of check that their proof was included in this super proof. What's the process for doing that, and what's the amount of computation that's required to do this superproof?
Yeah, so good question actually. So first of all, I mean, if you were to, let's say, talk about the process itself. So what's really happening is that you have, let's say, four different proofs coming from proof one, proof two, proof three, proof four. We basically have this. So in ZK proofs, there's this primitive called recursion. So what recursion really does is that it's proof of a proof. So a proof that is proving that a previous proof was actually valid, right? So what we do is that we create a recursive proof, which is proving that the previous four proofs were actually valid, right? So let's say you have, let's say, n different proofs coming from various places. So rather than every single proof proving itself, you have a single proof, which is taking all these proofs as an input and then create a single proof, which is again then validating all of them. So it's kind of, again, proof of proof, but multiple proofs kind of being combined together. So recursion as a primitive, and once you combine recursion at a multiple level, it kind of becomes aggregation. And the good thing is that proofs continuously get smaller. Obviously, there's a lower limit, but they continuously get smaller as you do more and more recursion. So you basically are able to come up with this really cheap way to verify proofs on Ethereum.
Okay, and
So
how
that's kind
many
of
proofs can you aggregate? Is it unlimited, or do you have like an upper bound of how many proofs you can aggregate into the superproof?
it really depends on schemes, but the one we use, which is Plonky 2, in our opinion, like you can like aggregate like infinite number of proofs theoretically speaking. So the limit of how many proofs you can aggregate is basically what are the number of machines you can access, or what sort of computation you can access. Because as you're aggregating more proofs, your computational requirements are going up. So what is that limit of how many machines you can get before you sort of run out of machines and you run out of that? So cryptographically speaking, mathematically speaking, there's really no limit. The limit really comes from how many machines you have.
Okay, and so once the superproof is created, then it's posted on chain, and anyone can verify that. Or so Ethereum is verifying this superproof, or like the destination chain is verifying the superproof.
Correct. Correct.
Okay, and then any application can look at that proof and sort of like take some action based on that proof being posted on chain and verified by Ethereum.
Precisely.
Cool. And so, like, what are the trust assumptions? So, as an application leveraging Electron's ZK proof aggregation system, I think, yeah, the universal proof aggregator. What are the trust assumptions that the applications have to have in order to use Electron?
Yeah, so I think there are sort of three areas, three possible sort of areas, right? So the first one is obviously, so the first question we get often is that, are they settling on us now as opposed to Ethereum? So the answer is no. You are settling on Ethereum. So think of it like this. It's more like proof ride sharing. Rather than you taking your own car to the destination, you're just taking an Uber along with us, right? So that's the only thing happening. You still get to the end your destination. The whole of you gets in the end destination. It's not like any piece of you is getting left behind in the car or anything like that. So the fundamental roll-up model or the settlement model kind of stays the same. The second question that you often get is that, what if somebody else's proof has a bug in it and gets hacked? Does that have a cascading effect on my proof if I'm using your aggregator?
Right.
So the answer is again no. The way we construct our layer is that all the other proofs in the layer that are getting aggregated can really fail, could have bugs, but your proof, as long as it's correct, really will be fine. So your application's security is not affected at all.
Okay.
The third one is that we do have our aggregation or recursion code that's really powering our infrastructure, which is something that if there's a bug in that, it will have an impact on your application, right? So you can say that our additional code, the recursion engine that we're adding is sort of the additional trust assumption. So any bug found in our code can really have that impact. So that's kind of the trust model here.
Okay. And in terms of, so we haven't really talked about the architecture of Electron, but like, is this proof aggregation happening on like a central server somewhere, or is there like a network of nodes that are constructing this proof so that we have sort of censorship resistance and liveness failure resistance? What's the architecture?
So as of today, it's a single machine that we are running. So we are not censorship resistant as of today. But of course, like our plan is to really have a proven network really doing this. In fact, Garvit is one company we're in touch with. They're building this decentralized proven network. where people just come in, really start running their own proving infrastructure, the aggregation infrastructure, and at that point, Electron team really disappearing will not have an impact on the infrastructure really staying up and continuing to operate. So yeah, short term it's centralized, long term we have a clear roadmap to really hand it over to the community basically.
Okay, so I'm actually curious about, if you could go into detail here on the sort of longer term roadmap. Is the goal to build like a dedicated Electron layer one that would do this proving aggregation, or to leverage some other infrastructure?
I would say again, so the reason anyone would be using a proof aggregation layer is because they're trying to get to the ultimate chain, which is Ethereum or somebody else in the end, right? So for us to have an L1 which is really adding those trust assumptions wouldn't really make sense. Having said that, there is an opportunity here where when it comes to these proof network, there's some sort of coordination required between all these people. There's some sort of batching required for all the proofs that are coming in. So we still need to create batches or blocks, as one can call them, to really and again have some sort of coordination among them. So there's some sort of you can say an L1 that doesn't really is not required for security purposes, but for coordination and liveliness purposes, right?
Yeah.
And eventually, yeah, I think in the long run, our network will start to resemble something like that, right? Uh, you know, yeah. So I think yeah, that's kind of the long term plan here. Yeah, yeah, yeah.
Okay, so I mean, I think what I'm getting here is that the utility of an eventual Electron network is more a liveness and censorship resistance feature than a security feature, because I mean we're talking about ZK proofs here, so obviously like the proofs that are generated are verified by the Ethereum blockchain or the destination chain, and so that aspect kind of disappears. In terms of coming back to the censorship resistance aspect, what then becomes the like how would these different nodes sort of coordinate? Like, would you have a I guess what I'm trying to get to is like, how do you incentivize nodes to stay online? Because like typically, if you look at a proof of stake network, we slash validators for producing bad blocks or censoring blocks. Although the censorship aspect, like if you look at a Cosmos chain, like you can be offline for some time, and like slashing is fairly limited. But if you want to have like a really high liveness network, you'd have to have some sort of an incentive for those nodes to stay online and to produce proofs very fast, I presume. So like, what's the mechanism here for incentivizing that and potentially like slashing those nodes if they were to go offline or censor proofs?
Yeah, I think at this point, probably having a token would really make sense. I mean, it's too early to kind of really, at this point, we really want to focus on the product, and token can sometimes be sort of a distraction. But
Yeah.
I do think that again, in the long run here, that as as the community really starts, that we sort of kind of disappear into the background, and the network for their own sort of confidence in their product, they would want that the network is really not dependent on us, and the network can kind of self-sustain without us being the Electron team really being kind of being the one tipping the balances, tipping the scales in kind of in the right way. So I think at that point, having some sort of a slashing mechanism or an incentivization mechanism using a token becomes really important, right? And again, like one thing I kind of forgot to mention here is that these people who are kind of using our network, they really need to pay a fees which is different than the fees that is being paid to verify these proofs on Ethereum. So these are two different things, right? They're paying a different fees. They're not paying the Ethereum gas fees anymore. They are paying a different fees now. So
Yeah.
there's probably an opportunity again, a need here to really have some sort of a like a gas model on Ethereum or some sort of a gas token maybe, which balances the demand of proof aggregation versus what is available on the Ethereum block space and what's the cost of verifying these proofs on Ethereum. So this kind of mechanism, I think a token is really well suited to have this kind of balance these two or three things out, which is incentivization, penalization, and balancing demand and supply. So that's kind of again, it's incredibly starting to look a lot closer to like being an L1 over a long enough period of time. Uh, yeah.
Okay. So you mentioned that you guys are using Plonky as a proof scheme. What are the other? Are there other compatible schemes like Snark or Stark or other types of proofs that can be aggregated or
Yeah.
that are compatible with Electron?
Yeah, so I mean, so everyone out there is using a different scheme, right? Some people are doing Halo 2, Grot 16, Plonky 2, Starks, all sorts of proof systems are there. So I think for us, it becomes really important that we support all proving systems. So we really can't be limited to one proving system because, everyone wants to access Ethereum block space. Everyone needs cheaper proofs. So the way we're really envisioning this in the long run, or even I would short to medium term, is that all proving systems or all proofs based on different proving systems should be aggregable. So we should be able to aggregate a Plonk proof with a Stark proof with a Halo 2 proof with a Grot 16 proof. So all of
Okay.
them should be aggregable, right? So it's again not been really done before. There's not much the kind of ideas in the ZK space how to really do that. But in my opinion, it's really an unsolved problem at this point. That how do you reduce all proof systems into a single proof system? So again, that's an experiment our engineering team, our ZK team is kind of doing internally. We made quite a bit of progress with Grot 16 and Plonky 2 and Starky interoperability with each other. Halo 2 is again something that's really on our timelines. How we want to do that? Yeah, we just kind of it's a question of roadmap and R&D how we do that. But we have to aggregate everything at the end of the day.
What's the biggest challenge like for like a total cryptography nimwit like myself? Like, what's the biggest challenge in aggregating these different proving schemes?
Yeah, I think the biggest challenge is we don't even know what we actually, it'll take to actually aggregate them. I think that's the kind of the biggest unknown here. But I think obviously there are cryptographic challenges that, for example, one proving system is using totally different kind of maths versus the other one, and how do you get the maths of one proving system to work inside the mathematical structure of the second one and vice versa. So that's kind of the cryptographic description of the problem, right? But I think there are many practical challenges as well. For example, within our team, for example, we have great expertise on Plonky 2 and Grot 16 and these kind of proving systems. But let's say we wanted to do Halo 2. Now we have no one in the team who does Halo 2. And you will not find anyone out there, I think, I mean, there are always exceptions that, but you'll have a hard time finding a cryptographer that understands all these proving systems with enough depth. So it becomes a very big hiring and team building challenge as well. But how do you actually get all this talent together? And again, a lot of times these different proving systems and people from these different communities, they also tend to be like politically disaligned with each other. They don't want to work together with each other. Those things kind of also exist. So it's really this technical, cryptographical, practical, political combination of all these challenges that one really needs to go through to make this happen. Yep.
How many like top tier ZK engineers or researchers are out there? Like, is it in the dozens, in the hundreds?
Yeah, it's a difficult question to ask. So I did this exercise in India once. Like I was able to count a total of 14 ZK engineers in India. Right?
Okay,
That's
so if there's 14 ZK engineers in India, a country of like over a billion, what does that say about the state of ZK? Yeah, maybe there's just a
I
low
mean,
concentration in India.
definitely very low concentration here. In terms of per capita basis, it will be higher in the US and Europe side. But I think
Yeah,
I think the number is definitely less than 200. Uh, and I think 200
globally.
will really, yeah. I think
Wow.
again, like if you start counting all the people in PhD programs across the world, that number is obviously a lot bigger. But like for example, somebody doing cryptography in some college, they might touch upon ZK. So again, how do you qualify whether they're part of the ZK community or not? But people who are actively working on the ZK space, either in academia or in the industry, I think that number will be less than 200 in my opinion. Uh, yeah.
Yeah. So basically, like all the people that have been on the ZK podcast, that's
Yeah, yeah, yeah,
that's
yeah,
the entire ZK community for the
yeah.
most part.
Yeah.
All right. Well, good job, Anna. So yeah, what's the like? Let's talk about the SDK a little bit. The Electron SDK. What is it, and how can applications leverage it?
So we haven't really had a chance to release the SDK itself. So kind of early days for the SDK itself. But so our philosophy for the SDK is that so we'll have this sort of infrastructure, right? Again, think drawing the Uber analogy, we'll already have a bunch, like Uber already has a bunch of cars running around, and people sort of just come in and start using this. So people kind of plug into the network and start using it, then exit the network. Similar model here, we'll have this aggregation network which will be up and running, and it will be aggregating proofs all the time. And anyone who wants to submit a proof can just send the proof to the network, and it will get aggregated and submitted to Ethereum. And our overall architecture will kind of make sure that you are able to extract your proof's specific information from our on-chain submissions. So you can kind of do that. Again, drawing the Uber analogy, the network does require a certain critical mass to exist in it for it to continue to make sense, right? So let's say if there's no one using the aggregation layer, then the cost of the aggregation layer really is the same as you submitting a single proof. So it doesn't really make sense. So again, the Uber analogy. So again, coming back to your question, so the SDK will sort of look like this, that we will give you this RPC endpoint, which will simply be accepting proofs from various people out there who want to submit proofs. And once your proof comes in, then we kind of handle everything else. We generate your proof, aggregate it together, and submit it on Ethereum. And then we give you certain pieces of on-chain APIs that you can call from and see that, okay, that your information is actually made to the blockchain. So again, so the SDK will kind of two parts: checking, sending the proof via the RPC endpoint, and kind of pulling the relevant information from the on-chain contracts. Yeah, so the integration process is really, it's quite simple actually on the high level. It might seem complicated, but it's really that simple. It's just sending a proof rather than broadcasting it to Ethereum or sending it to us. It's really that simple.
Okay, so as an application, you integrate the SDK. That just allows you to send the proofs to Electron such that they can then be aggregated and posted to the chain. I read something about that I wanted to ask you about, which is leveraging ZK proving in the browser, and this is something the SDK I think enables. Can you expand on that?
Yeah, no, so we don't do proof generation in browser, but yeah, happy to talk about browser-based proofs in general. So again, so there are, I think, two kind of schools of thought about browser-based proof generation. Some people are really trying to do distributed proof generation with some sort of intended effect on scalability side of things. Personally, I'm a bit skeptical of that. I mean, distributed computing based on leveraging people's individual machines, that never really took off. Like ultimately people the market really gravitated towards AWS and cloud-based systems. These ideas never work. And I think in ZK as well, it will not really scale ZK proof generation, in my opinion. The real reason why browser-based proof generation will take off, in my opinion, is for privacy, right? So if you're really trying to hide the data of your transaction, and you don't want it to submit it on chain, but you still want to leverage on chain, you need to generate your proof in the browser, because whoever generates the proof has access to all the data, right? So if you want to have a high level of privacy, you want to generate your proof in the browser. So I think one of the reasons browser-based proof generation hasn't really advanced as much as we would want is because privacy hasn't really advanced. As privacy as a market and kind of privacy products start to make sense, people will start asking questions that why are you generating proofs on a server which can then now see all of my data? So I want these proofs to be generated on my machine so that I really have that kind of privacy. I think that's how this market should really play out in the long run. Yeah.
Yeah, one application I see here is I've talked to some teams that are doing something in this area is ZK KYC. So the ability to kind of do some KYC right locally on your machine. So it could be, I think here you'd have to have some kind of an application, like either on a phone or maybe like a WASM application in your browser that checks the validity of some document. It could be like an ID or like your proof of residency document or something like that, and then generates a proof and then like submits that. So you can basically do your own KYC without having to share all of this personal data with some random company or like some random person, which you don't know the sort of security practices or if they're going to leak their data. I mean, like that happens. That still happens a lot, and then I think that becomes really interesting in terms of having compliant blockchain applications where you can have proofs that a certain user has been verified. So like in terms of Sybil resistance, that's like a huge application here, but also in terms of making sure that your users are in a compliant geography or jurisdiction or like something like that. I think that's one interesting application. I've also heard people talking about like having a validator in the browser and using ZK WASM and proof verification in the browser to be able to kind of create a distributed network of nodes. And this would be particularly interesting for like small communities that are like kind of bootstrapping, right? Where you have like an early number of users that aren't necessarily like professional validators, but want to run these machines. So it could be like for gaming or like some use case like this. Yeah, I wonder if you have thought of other use cases that might be interesting for like in-browser ZK proving.
So again, the use case you're describing here, I think, is more of a ZK Lightline use case, right? So somebody who's trying to verify, let's say trying to run the validator in browser. Again, too much computation, too heavy for a browser or a machine. So the idea is that you simply generate a ZK proof of the validator node and then verify it on yours. So again, so you're not generating a proof in the browser, you're verifying a proof in the browser. So this is an application of proof verification in the browser.
Got it.
Uh, yeah. Again, I have this kind of probably a bit too set of an opinion that browser-based proof generation is really for privacy application, like the one you mentioned. KYC is a great example. Like it's really a great example of this application. I personally have thought about this a lot. I don't see why would somebody generate a proof in the browser if you're not trying to hide the data. Just offload it to a server, man. Like it's just quicker. Yeah.
Yeah, I mean there is the censorship and kind of liveness aspect. So like perhaps you could have a like a fallback in the browser. Although this is kind of
Yeah,
like an
yeah,
edge case, right? Where like I mean most of these
yeah,
servers are online, but like for an
yeah,
application to have a fallback mechanism such that like even if the servers go offline or they're taken offline, maybe by like a government or a nation state, then one can still like do the proof themselves as like a last ditch kind of
yeah. You
effort
could say
to
that.
proof.
Yeah,
Yeah,
yeah, yeah. You could say that actually. I mean, it's like so you have single sequencer, you have multi-sequencer, and you have browser-based proof generation. So multiple levels of permissionlessness or censorship resistance, basically.
yeah.
Um, and browser-based being the ultimate one. Yeah, yeah. Interesting.
Cool. How are you working with like on your website? It says you're working with Gnosis and Near and Hyperlane and Router and a bunch of other teams. How are you working with these teams?
Yeah. So most of these integrations have been over the last 1 year. We've been building ZK-like clients or integrating existing ZK-like clients with their infrastructure. So for example, with Gnosis and Near, it has been building the ZK-like client for that chain itself. And if you talk about Router and Hyperlane, it has really been integrating existing ZK-like clients with their network. So again, Hyperlane and Router have this model where new security models can come in and sort of plug into them. And so the messaging layer kind of stays the same, and our kind of ZK Lightline security layer kind of integrates with that. So that's what these integrations are about. Again, lately we've been moving everything towards proof aggregation. So we plan to aggregate the Gnosis Light client, the Near Light client into the aggregation layer. That's something we've been discussing a lot with Gnosis team. Like one of the challenges that they have been facing with existing implementations of ZK Light clients is that they've turned out to be extremely expensive. Again, the gas cost verification. So that's something that we are planning to work, that we're working very closely with Gnosis on, that will just get the cost down significantly lower. Same with Near. And again, just kind of enable Hyperlane and Router to kind of leverage that infrastructure to really add security to their customer base. Yeah, so it's really kind of an adoption and business side of things really happening and playing out with this.
Well, that brings me to the next thing I wanted to talk about, which is interoperability and IBC. I think this is one of the big applications for ZK in crypto, and perhaps even sort of brings us to the end game, which I want to talk about a little bit later. But what are the challenges in bringing, say, a technology like IBC to Ethereum, and how does ZK solve that?
So bringing IBC to Ethereum has been, I think, uh, discussed since Cosmos has been around. It's if you go back into those early days, you still see discussions around that. And the challenge has always been that again IBC operates on this light client model, and as we discussed earlier, that Light clients are again still too expensive to verify on Ethereum because of the block space limitations. So it has always been a challenge. How do you get the Tendermint and the Cosmos light clients verifying on Ethereum? So more than a year back, Electron came out with this paper where we showed that you can generate ZK proofs of Tendermint light clients and verify them cheaply on Ethereum. So that has really kicked off a market in the last 1 year. We've seen teams like Union, Polymer, Sync, who really come up with these ZK Tendermint implementations to really make this happen, right? So this has been sort of ZK IBC 1.0. What people have been working with for quite a while, and has been, I think at this point, is quite well understood in the Cosmos community. But if you actually zoom out, you see that while these implementations exist, none of them have gone to production. None of them have gone to mainnet. They're all ready for mainnet. None of them have actually gone to mainnet. And nobody really talks about that. But in my opinion, the reason for that is that the moment you put these things on mainnet, the cost of proof verification will start to hit you. And there's no one out there who can pay millions in fees every month to really do that. So that is where our latest work with ZK-IBC, which we like to call ZK-IBC 2.0, really comes in. So ZK-IBC 2.0 is ZK-IBC plus proof aggregation, right? So what we are doing is, again, it's very straightforward. Rather than every single chain sending their own ZK Tendermint proofs on Ethereum and paying the gas fees, we can create an aggregate superproof for all of the Cosmos chains. So right now we have aggregated the top 4 chains in Cosmos, which is Celestia, Osmosis, Injective, and DYDX. So if you have 4 chains being aggregated, the cost that everyone is paying is 1/4. So this is live on testnet today. We recently announced this a couple of days back. But what we're doing now is really, so there are 62 chains that are on mainnet in Cosmos. So we are, we planning to expand our sort of chains that we're supporting very soon. And I think something to the tune of 20 chains will get aggregated now. Again, available via a single superproof. So if you have 20 chains, the cost that every chain is paying is 1/20. So you're paying 5% of the original cost. So 95% reduction will be available right off the bat to these Cosmos chains. And again, in my opinion, everything else can get solved. You can always have a better proving system. You can have better hardware. You can get the proving costs down quite significantly. And some of the late implementations have done that, recent implementations. But proof verification cost is a limiting factor, which is what ZK-IBC 2.0 will really solve for the community. Yeah.
Yeah, I think this is also kind of the idea behind Atomic IBC, right? Is to be able to aggregate all of the different IBC messages in Cosmos onto a single chain, and then that enables kind of asynchronous composability. Are you familiar with that?
Yeah, I have some idea. People are trying to kind of solve this problem in bridges in general. So I think Polygon's ag layer is kind of also trying to attack that problem from what I gather. So the idea is that everything will kind of settle on Ethereum via this aggregation layer. And the Ethereum, whatever settles on Ethereum becomes a source of truth. So you can sort of pull this data from Ethereum and you kind of know what has actually settled and what hasn't settled. So you're really trying to define a source of truth, which could be, to be honest, it could be Cosmos Hub as well. Like you could settle on Cosmos Hub. Again, I haven't really looked too closely on how Atomic IBC is happening, but been looking at what Polygon is doing. So I'm kind of guessing that that's what Atomic IBC is about, that we all try to aggregate source of truth in one place and kind of leverage off of that. Yeah.
Can you talk a little bit about, speak to the Union approach and the Polymer approach? Because I think those are the two teams, at least coming from the Cosmos side, that are most recognized as building this ZK-IBC. I think they now have a slightly differentiated approach where Polymer is focused more on the rollup space and Union more on the broader app chain space. How could ZK aggregation be leveraged by these teams to make the entire process more efficient?
Yeah. So I think so. If let's talk about Union particularly, I think I was looking at Comet BLS, which is the core product as far as I understand. So I think that leveraging the aggregate. So again, they already have using some sort of aggregation already. So I think one of the reasons they did that, if I'm not wrong, is that they introduced BLS signatures for their chain, and BLS signatures can be aggregated. right? So it's much easier to verify these BLS signatures on chain. I think that's the reason I think they did it, if I'm not wrong again. So they're kind of already leveraging some sort of aggregation, in my opinion. But again, in the long run, even verifying a single BLS signature is a little bit expensive. You want to get even that cost lower. And it's not just the signature, like you still have to verify rest of the headers. And as more sort of chain data comes in, this cost will probably go up. So I think there's an opportunity for Electron and Union to work here, that their Comet BLS proofs can sort of be integrated within the Electron aggregation layer, and then be submitted to Ethereum. So it will, I think together this can really make Comet BLS and Electron-based ZK IBC cheaper than Axeler itself. So Axeler itself is quite expensive if you want to go. I hear this often from Cosmos folks that it's super expensive. People, I think, paying north of $100 for going to Ethereum. I think together this combination of Comet BLS and Electron, I think, will make ZK bridging, ZK IBC cheaper than even centralized bridging. You know, so yeah, I think that's how Polymer Union could probably use that. Polymer had been lately. I think they're focusing more on the, as you said, roll-up side. I think earlier they were trying to do something around. They were trying to set up their own chain where they had changed some of the signature primitives to ZK friendly ones, which I think was an approach they abandoned later on. So hard to really point out. But again, I think they could. Again, they don't need to do that anymore. They could just send the proof to the aggregation layer and not, be leverage much cheaper costs right away. Yeah.
You said something really interesting here, which is that you think that ZK IBC could be even cheaper than centralized bridging.
Yeah. Yeah. So, I mean, so let's say right now, if you talk about the cost of proof verification on Ethereum. So the last time I checked, I think Axler was charging north of $100 for sending
Yeah.
transactions to Ethereum. I paid $80 myself. But if you talk about the proof aggregation layer, the cost of verifying transactions or proofs on Ethereum will become cheaper than $5, right? So $100 and $5. So it really becomes really, really much cheaper than what Axler is offering right now. And I think once you have higher level of security, the IBC level of security, and a much cheaper pricing model as well, I think it's really a very strong case for people using such a bridge as opposed to something like Axler, which is super expensive right now. Yeah.
Yeah, I think one of the other applications here for ZK IBC and ZK bridging generally is mesh security and restaking and like all of these applications that leverage the security of another chain and is able to verify the state of another chain, or at least verify that stake is securing another chain. Like, how do you see that playing out long term? And I guess, like, taking a step back here, what is the ZK proof endgame? Like, do we end up in a world where Ethereum is just like this massive ZK proving ZK verification machine that is just verifying proofs from all these different layer twos and other chains that want to leverage its security? Like, yeah, take us like far into the future here.
Yeah, I think I 100% agree with that. I think what's going to happen in the long run is that nobody will access Ethereum block space directly, right? Everything will happen inside a ZK circuit. And the only thing we'll do on Ethereum is verify these proofs, right? So the only function that the Ethereum virtual machine or all of this infrastructure will have is just verifying these proofs consistently. And we will be in a future where all the Ethereum block space, so if you go to Etherscan, if you look at a block and you look at all the transactions within the block, all of them will be just ZK proof verification. They will no longer be Uniswap swaps or simple transfer. They will just be ZK proof verification. And the reason for that is because the cost, the demand for the Ethereum block space is so high and it's consistently increasing that it's just not possible to access the Ethereum block space directly anymore. It has become really hard for users right now. I think in the long run, it will become hard for even application-specific rollups or the larger rollups for that matter. So I like to call ourselves as a ZK wrapper for Ethereum block space. You will access the Ethereum block space via this ZK layer and nothing else. And yeah, so you have like Ethereum block space here, and then you kind of zoom out this aggregation layer, which is offering you much more block space effectively. And on top of that, you have these rollups, which then again offer you much more block space, which kind of multiplying as you move up the layers. Yeah, I 100% agree with you on that. Just CK proof verification. Nothing else is required on Ethereum, in my opinion.
And do you see Bitcoin playing a role here? I know this is also like currently like it's impossible to do ZK proof verification on Bitcoin, but like Bitcoin is such a massive blockchain with like hundreds of billions of dollars of market cap and a potential for it to also secure lots of other applications. And we're seeing now like roll-ups on Bitcoin. Do you think that at some point Bitcoin could also secure, other applications and basically sort of like do this proof verification on chain? Sorry, I realized I said hundreds of billions. It's like, over $1 trillion of market cap. Yeah.
Yeah. First of all, I mean, I think everyone wants to see that happen. I think there's no question of that. We have also kind of experimented with building trustless bridges between Ethereum and Bitcoin in the past. We could never really solve that problem. I think Babylon chain is kind of really going places with respect to that. I mean, the protocol is definitely interesting, but I was also checking out some of the cryptographic primitives they're kind of playing around with. They have this thing called accountable assertions, which really leverage the limited cryptography that you can do on Bitcoin and leveraging that to really enable all these other sort of larger cryptographic pieces to happen. I mean, as you said, right now it's impossible to verify gross 16 proofs or ZK proofs on Bitcoin right now. But I think over time, better cryptography might unlock that. Again, I think we are very far from that. But there's some sort of, if you go really deep into the woods on the ZK side of things and talk to people who are really touching on things like FHE and all of that, there's some sort of early ideas as to how that might happen. That stuff is kind of a little bit too hairy for me as well. But again, I think it will eventually happen over a long enough period of time. I think where once you figure out if you can verify one proof every 30 minutes on Bitcoin, that's all you need. One proof every 30 minutes on Bitcoin. If you can do that, then you can build everything else on Bitcoin. Just that's all you need. Because then you can have aggregation layer to multiply that one proof every 30 minutes to large number of proofs. And when you have large number of proofs, you can have a lot of computation in them. So yeah, I think it will eventually happen. Not sure how, but yeah, fingers crossed on that.
Well, the time horizons with Bitcoin are always a little bit longer than with every other chain, but yeah, I think there's also like a huge potential here for Bitcoin to really serve as like an underlying security layer for a lot of DeFi activity and sort of blockchain activity generally.
Yeah.
And I think we're starting to see that a little bit now, and there's a lot more activity happening on Bitcoin. And as someone who's been in the space for a long time and like started with Bitcoin, it's something that I find really exciting.
Yeah, I love this idea of that everything else is an application layer for Bitcoin, basically. I love that notion. Yeah.
Great. Garvit, thanks so much for coming on today. It's been a real pleasure and I think a very interesting conversation. And looking forward to seeing Electron grow and become a larger part of the ecosystem and providing proof aggregation for applications across Ethereum and Cosmos and all other ecosystems. How can people learn more about Electron?
I think the best way is follow us on Twitter. We are at labs_electron on Twitter. You can join our Telegram channel as well, and which is ZK Electron, and we have a bunch of other dev chats. Would love to have you join them.
Great. Thank you.
Thank you. Thank you so much. Thank you for having me.